All right, so we're now moving into the mean value theorem and the first derivative test. This will correspond to assignment 20 and 21, one paper that covers these two topics. We will start out by discussing the mean value theorem. So anyway, let's suppose that we have an interval on the x-axis from A to B. I got to thinking this would mirror my trip to work from Auburn to Burlingame, let's say, all right? And so the idea would be you hit the south end of Auburn and you're at a certain position there, and wouldn't this be called f of A, right? So you're at that position A, f of A, and this is a graph of you traveling from Auburn to Burlingame. So as you left Auburn, you sped up, and then you had to slow down, and then you sped up again, and then you slowed down. So the point is you probably did not drive the same speed the entire time. You had some times when you sped up and slowed down until you finally get to Burlingame, and this over here would be called f of B, wouldn't it? All right, so let's talk about the mean value theorem. First of all, let's talk about visually what would represent your average rate of change. And this again would be the notes, Roman numeral number 1. Well, it turns out that your average rate of change would be basically the total distance you traveled divided by the total time it took. All right, and that would be visually represented by the slope of that secant line, you might recall. All right, and so the slope of that secant line there, that blue line, would be your average rate of change. And so, back to algebra again, y2 minus y1 over x2 minus x1, the slope of that blue line would in this case be f of b minus f of a over b minus a. And that would be your average rate of change. Let's say you averaged from Auburn to Burlingame. Let's say it's me driving, so you averaged 47 miles per hour. All right, that's pretty fast for me actually. But anyway, slow down out there, kids. You kids driving fast. But anyway, let's suppose I averaged 47 miles an hour over that trip. Does that mean I was traveling 47 miles an hour the entire time? No, definitely not. Sometimes faster, sometimes slower. Okay, so speaking of that, moving on in the notes there, so the slope of that's our average rate of change, that blue line there. So the theorem goes on to say that if we have a function that's continuous over this interval here, all right, so the implication there would be there's no asymptotes. For example, in my silly story, if there was an asymptote there, that'd be like we drove off a cliff, and the graph doesn't continue. Notice how many of our theorems assume continuity, all right? But if we travel in a continuous fashion, no asymptotes, no holes, we didn't drive into a pothole, something like that, okay, then here's the deal, and you have the notes already, there's at least one number, at least one value of c in this interval during our trip, all right? There's at least one place where the derivative at that c is the same as the slope of that secant line, all right? I want to remind you that this is instantaneous rate of change, slope of the tangent line, and this is average rate of change, the slope of the blue secant line there. And so the idea would be, if I averaged 47 miles an hour during the trip, what's this saying? If I averaged 47 miles an hour during the overall trip, there had to be at least one instant where I was going exactly 47 miles an hour. And again, visually, this is the slope of the secant line. This would be the slope of the tangent line. So, as we're traveling along here, think about slopes of tangent lines. It seems like maybe right there would be a place, maybe I missed it a little bit, but maybe there's a place where the slope of the tangent line is the same as the slope of the secant line. And so that place right there will be a value of c, where my instantaneous speed, my instantaneous velocity, is the same as my average, all right? And it says at least one. There could be one, there could be multiple, but as you continue on thinking about tangent lines, you might go, whoa, there's another place where the tangent line had the same slope. And that might be another value of C. And if you had more than one, you might call them C1 and C2 and so on. Oh, there's another instant where we were traveling the exact same, and so on. And maybe here's another one, where the slope of the tangent line was the slope of the secant line. But this theorem guarantees there's at least one, and there might be multiple. So the point would be, if I average 47 miles an hour from Auburn to Burlingame, average, the blue one, there had to be at least one instant where I was going exactly that same speed. All right, and so, you know, you can read the notes here. If we have a continuous function, there's got to be at least one place where the slope of the tangent line, f prime of c, is equal to the slope of the secant line. And there's multiple ways to say that. There's got to be at least one place where your instantaneous rate of change was the same as your average rate of change. There's all kinds of things related to that. And of course, we always make sure that the function is continuous before we apply the theorem. Otherwise, all bets are off. If there was an asymptote or a hole in there, the theorem is moot. So anyway, that's an introduction to the mean value theorem. And now we will go and apply it to a couple of specific functions and specific intervals. Again, keep this picture in mind.